All right, guys. So, welcome to a workshop on introduction to OpenFOAM. My name is Sarang, and I'm going to be the presenter, as I mentioned earlier. A little bit about my background. I completed my master's at the University of Wisconsin-Madison, where I specialized in CFD and combustion. After which, I worked in the US for the last 6 years as a senior research engineer in a company called Convergent Science, where I used to work with several OEMs like General Motors, Ford, Hyundai, on their internal and external flow projects. So what are we going to be looking at today? We are primarily going to be focusing on, what is CFD and, what is OpenFOAM, right? I will be talking a little bit about SkillLink because I'm pretty sure some of you might have not heard of us. So I'll do that. And then we'll directly, jump into the conversation, talk about CFD, talk about OpenFOAM. Now, remember, this is an introductory level presentation. Okay. The primary goal here is to introduce all of you to CFD. And don't worry, this is a practical workshop, meaning you will be learning something useful today. So the workshop is also being recorded, and you will be sent the recording along with your certificates. And when we do that, you will be able to watch the video and maybe practice some commands, install OpenFOAM along with it. A little bit about SkillLink. So SkillLink provides advanced project-based engineering courses. We primarily focus on mechanical, aerospace, and automotive engineering courses. And we do this by partnering with industry experts. So only in SkillLink can you take courses that are instructed by subject matter experts who work in companies like General Motors, Tesla, Hyundai, and so on. And we pride ourselves in teaching skills that matter, meaning we create courses in areas that are currently being used in the R&D space in many industries. And that is why we have students from really popular engineering colleges taking our courses, like your IITs, JNTU, PhD Tech, College of Engineering India, and also some US universities. All right, so let me just directly jump to the topic. So first of all, what is OpenFOAM? So OpenFOAM, as I mentioned, is an open source computational fluid dynamic package. So what does open source mean? At the end of the day, every computational fluid dynamic software that is there, like ANSYS Fluent, Star CCM, Converge, OpenFOAM, at the end of the day, it's a computer program, meaning someone has coded it using C or C++ or Fortran, right? Using one of those programming languages. ANSYS and Star CCM, for example, are commercial softwares, meaning these are not open source. You cannot see what's going on behind the screens. For example, in ANSYS, if you're setting up a case, you don't know what is happening in the background. How is ANSYS creating the mesh? What are the techniques it's using? And when ANSYS gives you the results, for example, it says that, okay, in the case of my pressure valve, so for example, this right here, you have a gate valve. In this particular valve, what is the pressure loss or what is the maximum maximum velocity, right? You cannot cross-check by looking at the equations to make sure that the answers are correct or not. So this is what you call as a closed source, meaning the code or the entire program is hidden from the user, and that is their intellectual property. In case of OpenFOAM, everything is open. So not only can you take a look at the source code and try to understand how they have coded all the coding algorithms, meshing algorithms, turbulence algorithms, you can actually change it, and it doesn't stop there. You can actually use it for commercial purposes, meaning say that you're designing a car, you are having a small car company or an electric vehicle startup company. To perform external aerodynamic simulations, you cannot use ANSYS Fluent legally, but you can use OpenFOAM, and not only because it's open source, because it is also capable, and that is why open source is so popular. It's a free tool which is as powerful as ANSYS Fluent, and that is why it is so popular with companies. And you can solve a lot of problems. You can look at external flow dynamic problems. You can look at interface tracking problems. So for example, here you can see that there is a fluid flow that you're tracking. This is what you call as the interface tracking, because the box is filled with air and some kind of a fluid, right? And you're tracking where the fluid is. So that is what you call as an interface tracking problem. Discrete phase modeling, meaning you actually have these parcels and you're basically trying to simulate how these parcels interact and how these parcels actually move around in your computational fluid dynamic space. And in addition to this, it can do much more. For example, it can do incompressible flow simulations. So for example, this right here is a propeller. So this can be a propeller of a ship, and you're actually looking at how the velocity is, as the propeller rotates. And this is your classic valve example. So the nice thing about the valves are that you basically look at what's the pressure loss. This is one of those simulations that are being done left and right. Like pretty much every company that does flow analysis does this.